In this video lecture, we look at differential equations, the applications of differential equations. Differential equations, as was discussed in the last video lecture, has extremely wide applications in virtually every aspect of our lives that involves some sort of rate and anything else, even applications in economics, accounting, obviously all the sciences, any physics and mathematics. But we're going to look at applications, growth and decay. Now, in reality, we get so many different situations where we see growth and decay. You take, for instance, a population of a city that grows at a certain rate. Or you take any decaying tree, for instance, a tree that dies. It decays over a period of time. What we are basically looking at here is trying to identify at what point, either in growth or decay, will the substance that is either growing or decaying be at a certain quantity relative to its original amount. So, for instance, I may start with some sort of, in physics, an isotope of any particular element, and let's say we have a kilogram of it, and it starts decaying. Then after 10 years, we would like to know, well, how much has decayed and how much remains. Now, before we get on to the actual growth and decay, let's just quickly look at an introduction. This is simply the notes that I've placed on Moodle, and this is the explanation. So it will go through a little quicker. Most physical systems can be studied from a mathematical point of view. We need to look at variables and constants, look at the physical laws that govern the behavior of that system, and we can formulate a differential equation which we can then solve using standard analytical techniques. What's our standard techniques? Those that we discussed: differential equation methods, the two separable, linear. There's also others. We can get homogeneous equations, we can get Bernoulli equations, we can get a number of different ways of solving differential equations. And then we've only touched on differential equations. We looked at ordinary first order differential equations. We get second order, we get partial differential equations. Fortunately, we're not going to look at those in this course. But to construct a differential equation, we need to look at relations that are used. So, for instance, you've come across this in your physics in school. If A is directly proportional to B, how do we write that? A proportional to B. How do we formulate an equation? We introduce a constant and we say A is equal to K times B. If A and B are inversely proportional, we say A is proportional to 1 over B, introduce a constant to make it an equal to sign, A is equal to K over B. Now the one that we're going to concentrate on is number 3, the rate. Now as soon as we look at rate, what are we looking at? With respect to time. The rate at which A changes is directly proportional to B. So A changing with respect to B What are we looking at? dA dt proportional to B. Introduce your constant, dA dt is equal to K times B. Now that's going to be the backbone of this particular lecture to derive a formula. So let's look at growth and decay. Many physical systems are either growing or decaying. This particular law. Now this is a most important statement. The rate of change, whether it's growth or decay, is proportional to the amount of substance present at a particular time. The rate of change is proportional to the amount of substance. So we know about rate, bring in proportional and the constant and the amount of substance at a particular time. This law generates a differential equation which can be solved. So here we're going to look at this derivation. We're going to arrive at a formula that we're going to use. So we're going to introduce N. I'm going to use N. Other textbooks and lecturers may use a different letter. I'm using N for number. So let N be the amount or the number of whatever quantity we're looking at present at a time t. Then the rate of change of N is proportional to the amount present at time t. That is, the rate of change in dt is proportional to N. Introduce your constant K, dN dt is equal to Kn, and this is your differential equation. Now think carefully. dN dt is equal to K times N. We know that K is a constant, so it's dN dt, and we have N on the right-hand side. This is a differential equation. We need to find N. In other words, we need to find a solution of this differential equation. There are different ways and methods of solving a differential equation. We got separating variables. We got a linear equation. What is this? This is a simple separating equations. I can leave the dN on the one side, divide by n, and cross multiply with the dt, and then I have on the left hand side only n's and dn's. On the right hand side I have dt. Of course k is a constant, so that is a number. I can leave that. And now I integrate. The integral of the left hand side is equal to the integral of the right hand side. And what's 1 over n? The integral of 1 over n, ln of n, plus kt is equal to k times t, the integral of dt. Remember the integral of dt, that's equal to t, and I've got k in front of that, so that will be a k times t, and I've introduced my constant as c1, and that is the solution to the growth and decay question. That is the formula. However, I'm going to write this in another way. And the reason is I know many people have problems with logs, but you shouldn't have at this stage. Nonetheless, I'm going to go a little further. If ln of n is equal to kt plus c1, to eliminate ln, I introduce my exponents. So it'll be e, but it will be the entire right-hand side goes into the index. Now I'm going to write another step here. I'm going to separate that, e to the power k t times e to the power c1. So I'm just using my exponential laws to split. Remember, e belongs to kt as well as c1. Multiply is a constant, e to some constant. I've introduced that as my c, and there's e to the kt, and this is the formula that I'm going to use when we are confronted with questions of growth and decay. Remember this, the N you see there is the amount of substance remaining, the quantity of substance at a particular time. So this is the derivation. You should know this derivation. And that is the formula that we have arrived at. Let's look at, before we look at the example, we can discuss what we call half-life. Now, the half-life of something is a time. So if you take something that is decaying, the time taken for half of the substance to decay is known as the half-life. That means if half of the original substance decay, half remain. Now, this is an important concept to understand, firstly, because its application is widespread. We know about the nuclear, radium, plutonium, and how it affects so many people, objects, nature after a nuclear explosion. And why is that so? It's simply because the element that is used, whatever it is, remains decaying for a very long time. And we need to understand and know how long that particular element will continue decaying. Now, not only in nuclear explosions, you could take, for instance, in nature, where an animal in a game park, for instance, dies, and then predators will feed on it. But there will come a time where it starts getting poisonous. And there you need to know, or researchers will probably try and identify how long that takes before it starts being poisonous to predators. Now we can get many other situations, but I'm not going to go into that. Let's rather look at the derivation of the half-life formula. So let N be the amount of substance remaining. Look at this carefully. N is the amount of substance remaining. And N0, subscript 0, is the original amount. Now this is growth and decay. So from our growth and decay formula, let's just go back. There's our formula. N equal to C e to the power kt. At t equal to 0, in other words, the original from the starting point will allow t equal to 0, the original amount, then this C is equal to N0. So I can substitute into this equation. I'll notice, of course, when I do that, N0 is equal to C. How is that so? Just put t equal to 0 and n equal to N0, and I get C is equal to N0. And there is an equation which we can now use that relates original amount. So N0 is the original amount. and N is the amount remaining at a particular time. Now, another way of putting it, I'm just going to write this there. N is equal to N0 e to the power kt. I can divide by N0 and I get N over N0 is equal to e to the power kt. Now, some textbooks also use this form, and you may use it as well, because this is a fraction where N is the original amount, sorry, N0 is the original amount, and N is the amount remaining. So that gives you an idea of the fraction. Now, for half-life, I'm going to use T half to indicate the half-life. And because we're dealing with half-life, the amount remaining must be half of the original amount. Look at that carefully. N is the amount remaining. N0 is the original amount. Therefore, N over N0 must be equal to a half. And that's what we substituted into this equation, yeah? N is a half of the original amount. The N0s cancel. I'm left with a half e to the power k t half. In other words, that t over there is specifically for the half-life. And now, if I want to find t half, there's a e, what must I introduce? Ln. So ln of half is equal to kt half. T half is equal to ln of a half divided by k. You know where that comes from. Negative ln 2. Ln of a half is equal to ln of 2 to the minus 1, which is minus ln of 2. That's where I got that. And that is a formula for half-life. In other words, if I know a k value of a growth and decay problem, then I can work out the half-life, which is the time taken for half of the substance to decay. Now, this is a derivation for half-life. Follows very closely on the previous derivation. Now, at this point, you may need, I would say, another viewing to really understand the depth and significance of half-life. It's manipulation of the formula and knowing exactly what we are talking about. So yeah, I must reiterate, as the amount of substance remaining, N0, the original amount. And if a half remains, obviously the fraction N over N0 will be equal to a half. So just to recap at this stage, we've got two formulas to consider. The normal general formula, N equal to C e to the power kt, where we have, which we can use at any time, at any point in the growth and decay of a substance. And then secondly, we have the half-life, where we use when we are asked to work with the half-life, where we know it's a time taken for half of the substance to decay. Right, we only have one, or do we have two examples? I think we have two examples. Let's look at the first one. Suppose that the number of bacteria rose from 200 to 2000 in 8 hours. Now the next statement sets the tone for this problem. The next sentence, if the rate of growth of bacteria is proportional to the amount present. In other words, when we look at any growth and decay, the rate at which it grows or the rate at which it decays depends on the amount present at a particular time. That's how we generated these formulas. It's proportional to the amount of substance present at a particular time. So that's a very important statement. Now, why do I say that's an important statement? Because if you look at the rest of the question, find the number of bacteria present after 4 hours. So if you simply ignore the statement that the rate of growth is proportional to the amount present, many people will say, oh, that's easy. If 200 went to 2000 in 8 hours, then in 4 hours, I'll just find the midpoint. Well, unfortunately, that does not happen because the rate of growth is proportional to the amount present. To give you a very simple case, suppose we start with two bacteria. And the next time we look at it, it doubles for 1 hour, 2 hours later, it doubles, 8. 3 hours later, what is it? And so on. It's virtually exponential. So we can't simply take a midpoint and say, okay, that will be halfway between 2 and 32. It doesn't work. The only way to look at this is, of course, what we're doing right now. Just the next slide. I just want to erase that quickly. I don't want to emphasize that at all. Right, getting back to this. So that statement becomes important. Now, what's our solution? So this is the question. In our solution, you're going to introduce an n. You're going to say let n denote the amount present at a given time t. And when you do that, then you can write down the equation n is equal to c e to the power kt. Unless I tell you to actually derive it, then you'll have to do what we did in the first slide. You'll have to do this. If they don't ask you, then we can go straight onto the example here. Now, we have two pieces of information. It says the bacteria rose from 200. So N was 200 when? It was 200 when we started our observation. In other words, when T was equal to 0. Then it rose to 2000. Then N was 2000. After how many hours? 8 hours. Just going to pause here. And try and get back to why I'm hearing this sound. Just give me a moment. It's more my headphones that need to be recharged. So I'm going to connect here. Okay. Apologies for that. Let's get, let's continue from our current slide. Right, so we have two pieces of information. We started with 200 and we can say let the base, in other words, we start at the countdown when t is equal to 0. After T equal to 8 hours, we get N equal to 2000. Now, does that ring a bell? You've done this in school. Two pieces of information, two unknowns. What are we dealing with? Simultaneous equations. So we're merely going to substitute into equation 1. Take the first case, T0, N0. There's N, 200. There's T, e to the power 0. What's e to the power 0? 1. I get C is equal to 200. So replace the C by 200. Therefore, N is equal to 200 e to the power kt. Many people start from here, and that's fine, as long as you understand the equation that you write down. Now, what are we looking for? What is the value we need to calculate? We're looking at K. If we get K, then we have an equation with N and T, and I can find any value after that. So what do? Substitute the other piece of information. What's N equal to? 2000. What's T equal to? 8K. Divide by 200. What must I introduce? Ln. What's K equal to? Ln 10. Divide by 8. And please be careful. It's the entire ln 10 divided by 8. It's not ln, open brackets, 10 over 8. It's open brackets ln of 10, then divide by 8. There's my answer, 0.2878, correct to 4 decimal places. Now that we have the value of K, we substitute it back into this equation, because for this particular problem, that's 200, the K value is ln of 10 divided by 8 in the exponent, and there's my T. Now I can answer the question. What is the number of bacteria present after how many hours? 4 hours. Substitute T equal to 4. In other words, T of 4. Put my 4 in there. Do my calculation. And there's my answer. Correct to 3 decimal places. So I get 632.397. Of course, we can round that off. Bacteria, 132 complete bacteria. And that is certainly something that you must be aware of. If, for instance, we are dealing with population, then we're dealing with people. So you get 632.397. Obviously, we don't have 0.397 of a person. So we'll take the closest whole value. There's your example. Now, all the examples on growth and decay, follow this pattern. Start with an equation, look at the information given, do the substitution. But they also like to put in percentages as well, and ratios. And that ratio comes from the ones that we looked at previously. N over N0, for example, was a half. Maybe it's a 60%. So instead of being half, 0.6. In other words, the amount remaining to the original amount could be any percentage. In this case, it's a half. It's 50%. It could be 60%. It could be 10%. It could be 90%. 0.9, 0.1. So read the question carefully. Now, I'm just going to do one more example. And here I have the solution. Assume that radium disintegrates at a rate proportional to the amount present. If 100 milligram reduces to 90 milligrams in 200 years, how many milligrams will remain after 1,000 years? And find the half-life of radium. Again, if you look at this, firstly, the statement, proportional to the amount present. Therefore, you're definitely dealing with growth and decay. Now, over here, I merely went through the derivation again, but we're going to use that formula. Let's see. Do we have pieces of information? 100 milligrams reducing to 90 milligrams. So we're starting. This is our beginning point. And that's how many remains. After how many years? 200 years. So at the beginning, we're going to make t equal to 0. So t is equal to 0. How much do I have at the original? 100. Substitute 100. E to the power 0 gives me c equal to 100. Therefore, for this particular example, I can use this equation there. N is equal to 100 e to the power kt. What is the other piece of information? 90 milligrams. So after 200 years, 90 milligrams, substitute into N, into T, transpose, work out the value of K. I get K, and I've taken to 1, 2, 3, 4, 5, 6 decimal places. Now take that value, substitute it back into there, because that's the equation that you can work with for this particular problem. So I get 100 e to the negative 0.0000527 t, and now I can answer the questions. How many milligrams will remain after 1,000 years? T is 1,000. Substitute 1,000. I get 59.037. Therefore, 59.037 milligrams of radium will remain after 1,000 years. Now, I want you to think about it. Try and put that in perspective. Try to put it your lifetime. That's why nuclear explosions and anything of that nature is really something that we should try and avoid. We started 100 milligrams, reducing to 90 milligrams. And that took how many years? 200 years. After 1,000 years, 59 milligrams still remain. And they are disintegrating, giving off the deadly rays. Let's go to the next part of the question. Find the half-life of radium. Well, very simply, for T half, we know that our equation, so this is the equation that I'm going to work with. Over here, we know that half of N0, half of the original, is equal to N0 e to the negative 0.000527. The N0s cancel off. A half is 0.5. Introduce ln, and I get 1,315.27 years. And there you go. That is the type of problems that you will be confronted with growth and decay. Possibly, I should just look at giving you another description here. How this was obtained in, that's the amount remaining. That's the original amount. We know this formula for half-life. We can go back to that formula. There you go. N is equal to N0, e to the power kt. I'm using that equation. E to the power, but now we know exactly what the value of k is. Negative 0.0000527 t. I'm going to divide the original, so I get the amount remaining over the original is e to the negative 0.000527 t. And for half-life, what's this equal to? 0.5, which is what you see here. And then we can do the rest of the calculation, introduce in ln, and we get the final answer, t is equal to 1,315.27 years. That's the end of this lecture.